Today we're going to be solving problem 3.22, which says in problem 2.25, you found the potential on the axis of a uniformly charged disk, as shown below. Use this together with the fact that the Legendre polynomial of 1 is always equal to 1 to evaluate the first three terms in the expansion, equation 3.72, which I'll rederive, for the potential of the disk at points off the axis, assuming that they are a distance greater than the radius of the disk away. So that means that we're going to be looking at points far, far away from the disk over here. Just say r greater than r. So to start with, we can take the general equation for the potential, v of r theta is equal to a summation from L equals 0 to infinity of a sub L r to the L plus b sub L over r to the L plus 1 all times the Legendre polynomial of cosine theta. Now, because we're dealing with points far outside of the disk, the first boundary condition that we have to account for is that as r approaches infinity, the potential must go to 0. And the only way that this is possible, as we're familiar with from other questions, is if a sub L is equal to 0, because otherwise it would blow up. So that leaves us with v of r theta is equal to the summation from L equals 0 to infinity, b sub L over r to the L plus 1 times the Legendre polynomial of cosine theta. Now the second boundary condition that it gives us is it says that at theta equals 0, the potential has to be equal to this. Now generally when it gives these kinds of equations, what you're looking for is how you can write it in terms of the Legendre polynomials, which makes finding your coefficients a lot easier. So also an important note is that at theta equals 0, we do have to deal with this, the Legendre polynomial of 1 equals 1, and I'll go ahead and prove that. So, of course, at theta equals 0, you have the Legendre polynomial, the cosine of 0, which is just equal to the Legendre polynomial of 1. Now, the first couple of Legendre polynomials, assuming our variable is x, the 0th Legendre polynomial is 1, the first Legendre polynomial is x, and the second Legendre polynomial is 3x squared minus 1 divided by 2. So now if we plug in x equals 1, if we plug in x equals 1, this is still equal to 1. This second one is also just equal to 1. Now the third one, you plug in 1 and you get 3 minus 1 divided by 2. That's also equal to 1. So we can say that P, Legendre polynomial of 1, is always equal to 1. Great. Now with that said, we can rewrite the boundary condition that it gives us. So we can say V of R0 is equal to summation from L equals 0 to infinity of B sub L over R to the L plus 1. Oh, actually, it's important to note, this is valid for R greater than R. We said that at the beginning, but just to be clear. And to go back here, writing this is kind of redundant because it's just equal to 1. So I'm going to go ahead and leave it off. And that is going to be equal to sigma That's a poor sigma. Sigma over 2 epsilon naught times the square root of r squared plus big R squared minus r. Cool. So at first glance, writing this in terms of Legendre polynomials kind of looks like a nightmare. However, because we are looking at cases where r is far greater than r, we can go ahead and well, I mean, we could do this either way, but we can go ahead and factor out an r. So that will give us sigma r over 2 epsilon naught times the square root of 1 plus r over r quantity squared minus 1. So what we're setting up to do here is because we are using r is greater than big R, little r is bigger than great R, we can use a Taylor series approximation. In particular, we're using a Maclaurin series approximation, which is just evaluating at 0. And we are going to be taking this bit here, actually. And we are going to treat it as the square root of 1 plus x, where x is equal to big R over little r quantity squared. Now, as a reminder, the equation for a Maclaurin series is the summation from n equals 0 to infinity of the nth derivative of the function evaluated at 0 divided by n factorial times x raised to the n. And now, in this case, our function is 1 plus x. So we can say first, at n equals 0, we just have the 0th derivative, which is just going to be 1 plus x to the 1/2 times x to the 0 over 0 factorial. This is just 1. And this gets evaluated at 0. We'll say this whole thing evaluated at x equals 0. And that is just going to be equal to 1. Now the second one, n equals 1. And now we're going to be doing the first derivative, which will give us 1/2 times 1 plus x raised to the minus 1/2. Evaluate that at x equals 0. We're going to be multiplying that by x to the 1 over 1 factorial. This is just going to become 1/2. And this is just x. So this gives us just x over 2. Now the third term, n equals 2. So now we're taking the second derivative. We can just go ahead and take the derivative of the one that we found before. And we will get minus 1/4 times 1 plus x raised to the minus 3/2 evaluated at x equals 0. And evaluating at x equals 0 is honestly really nice because, you know, the other term being 1 in here, raise it to any power, it's just 1. That makes it very simple. And that's going to be multiplied by x squared over 2 factorial, which is just 2. And this is just going to be equal to minus 1/4. And this is just going to be x squared over 2. So this whole thing is just going to be minus x squared over 8. Sweet. So now we can go ahead and rewrite this in terms of what we have. So actually, if we just plug in x, this is still going to be 1. This is going to be 1/2 times big R over little r quantity squared. And this is going to be, well, actually, I guess I can write it out explicitly. R squared over little r squared. And this is going to be minus 1/8 times r to the 4th over little r to the 4th. Okay, now we can go ahead and plug these back in here. So we have this equation sigma r over 2 epsilon naught times 1 plus 1/2 r big R squared over little r squared minus 1/8 big R to the 4th over little r to the 4th and minus 1. And we're just doing the first 3 terms. After that, it doesn't really matter. So, and this is great because then the 1's cancel, and then we can go ahead and factor this r back in, and we end up getting sigma over 2 epsilon naught times r squared over 2r minus 1/8, well, actually, just say r to the 4th over 8r cubed. Great. So we can already see this taking form. If we look back at our potential equation here, you've got some constant over some power of r, and that's essentially what we're getting to. So now we can say, again, v of r theta equals, shouldn't be theta, v of r at 0 is equal to this summation of v sub l over r raised to the l plus 1 from l equals 0 to infinity, and that is equal to sigma over 2 epsilon naught r squared over 2r minus r to the 4th over 8r cubed. Great. Actually, you know what? To make this a little bit more obvious, here's what I'm going to do. We're going to write out the first couple of terms. So at L equals 0, we get b of 0 over r. Next term, b of 1 over r squared. The third one, because the question says evaluate only the first 3 terms, b sub 2 over r cubed. And that is equal to sigma r squared over, actually that should be 4. 4 epsilon naught r minus sigma r to the 4th over 16 epsilon naught r cubed. Yeah, perfect. So, I mean, as we can see here, we do have something with a power of 1 over, or something with a factor of 1 over r, something with 1 over r cubed, but nothing with 1 over r squared. So we can pretty much directly say, just by looking at this, that b of 0, or b0, is equal to sigma over epsilon naught r squared over 4 b1 is equal to 0, which is why there's no 1 over r squared term. And b2 is equal to minus sigma r to the 4th over 16 epsilon naught. Great. So now we can go back to our original equation again and expand that out. So we can then say v of r theta is equal to, and because these both have the common factor of sigma over epsilon naught r squared over 4, I'm just going to go ahead and factor that out. So it'll be sigma over r squared, or sigma r squared over 4 epsilon naught times, and this is going from this general equation here. So we will be including the Legendre polynomials. Actually, maybe let me make that a little more explicit. So equals the summation from L equals 0. Actually, no, because we're only doing the 3 terms, so it doesn't really make sense to do the summation. But that is the general equation that we're using, and so there will be the Legendre polynomials accounted for there. So sigma r squared over 4 epsilon naught times the 0th Legendre polynomial cosine theta over r minus r squared over 4r cubed times the 2nd Legendre polynomial cosine theta. So then we know that, I mean, we kind of mentioned it earlier, but the Legendre polynomials, this will then become, you can factor out a 1 over r, and this becomes b of r theta is equal to sigma r squared over 4r epsilon naught times the 0th Legendre polynomial of cosine theta is just 1 minus yes, 1/8 big R over little r quantity squared times 3 cosine squared theta minus 1. And this is true for little r greater than big R. And this is our final answer for part A. Awesome. Thanks so much.